To run large language models locally on a mobile phone, we run into an immediate physics problem: memory bandwidth. During inference, the GPU has to fetch every single weight of the network from VRAM to its execution units to generate a single token. This diagram illustrates how those weights are stored. In their unoptimized state, a model's parameters exist as 32-bit floating point numbers. They span across a continuous mathematical coordinate plane, packed with infinite decimal precision. Mobile chips lack the capacity to sweep billions of continuous 32-bit values 50 times a second. We must map this continuous space into a discrete 8-bit grid. Deploying AI natively to mobile devices is not solved by waiting for larger phone RAM. We have to mathematically force a continuous coordinate space into a rigid integer cage. We calculate scale S, dividing bounds alpha and beta by integer limits, stretching the grid around our data. The 0 point Z slides the origin, locking the grid in position. Finally, a clip function forcefully slides outlying points to our strict integer borders, preventing overflow. By executing this 3-step scaling, translation, and clipping pass, we shrink the memory footprint of the model by a factor of 4. We sacrifice endless decimal precision to guarantee the model fits entirely within the mobile processor's structural memory limits. Let's apply those formulas. Here is an unquantized 2x2 matrix of real floating point numbers, stationed directly alongside our scale and 0-point parameters. Applying the scale division and origin shift, the continuous numbers independently snap out of floating point space and lock into discrete 8-bit integer forms. This localized matrix transformation is the core geometric shift. Extending this operation across billions of parameters allows massive network architectures to execute cleanly inside the tight memory confines of an edge device. Compressing the data into an integer format is only half the process. We now have to map that newly discrete geometry directly to the physical silicon of the mobile processor. This diagram represents a single 128-bit hardware execution pipeline inside an ARM Neon SIMD architecture. A standard loop forces a CPU to process data sequentially, one instruction per element. SIMD stands for Single Instruction, Multiple Data. Because we mathematically shifted from wide 32-bit floating numbers down to compact 8-bit integers, this single 128-bit hardware register naturally divides. It cleaves perfectly into 16 distinct parallel mathematical lanes. We can now route our previously quantized integer blocks straight into these physical architectural lanes. 16 distinct data points load side by side perfectly into a single hardware register. The physical advantage of this geometry happens at the exact moment of computation. In a single hardware clock cycle, the processor sweeps across all 16 lanes simultaneously, computing an entire cluster of dot products instantly without looping. Tracking the entire architectural journey, we take continuous floating point parameters, compress them with a spatial scale and 0-point shift, and feed the resulting discrete blocks precisely into the parallel lanes of the SIMD register. Shrinking the file size of the model is a secondary benefit. True on-device execution speed is achieved by manipulating the spatial geometry of the math so perfectly it exploits the exact physical lanes of the hardware.